Okay, so continuing with the second line of defense, there are cells that are phagocytes, and they kill by phagocytosis, by surrounding a cell or a pathogen and then creating a vesicle, a food vacuole, if you will, which then fuses with the lysosome. And the lysosome, by the way, is an organelle. Lysozyme is a secretion or is an enzyme that breaks down bacterial cell walls. So that can be a point of confusion. But remember, lysosome is an organelle inside the cell. That just the names are very similar. But in any case, you have other ways of killing things that don't involve phagocytosis. So non-phagocytic killing would basically be where these different types of leukocytes, one is a type of lymphocyte, which you remember is agranular, and then neutrophils and eosinophils are granular. But in any case, what they do basically is they recognize, they come next to a cell, they're able to move and come next to a cell that they want to kill, and then they secrete out something, and it just kind of spills onto the surface of that nearby pathogen. And the way natural killer cells do it, they secrete out toxins onto the surface particularly of virally infected cells. So natural killer cells are typically associated with killing cells that are infected by virus. In other words, they're killing your own cells, but they are virally infected cells. So there's a trade-off where, if one of your cells is infected by virus, it has to be killed for the sake of the entire organism. Now, sometimes this gets a little overactive, and you can actually have some pretty serious damage that's caused to an organ when a lot of its cells are killed, but still the virus has to be killed, and the only way to kill the virus is really to kill the cells that are infected, because you know how a virus reproduces. It reproduces inside of the host cells. And then it also acts against tumor cells. I think you may not be aware that your body does have some defense against cancer. In fact, we're starting to realize that the body actually clears more cancer than we originally realized. So, the fact that you don't get cancer doesn't mean you never got it. It just means your body was able to get rid of it, probably. That's what we now believe. But in any case, those are natural killer cells. Neutrophils, they also can secrete chemicals that can kill cells. Mainly what they do is they create and secrete these fibers, which is kind of cool because it makes like a net, and the acronym for this is NET, Neutrophil Extracellular Trap. I think that was on purpose. But they created this acronym here to describe this fiber that they secrete, and it kind of traps bacteria, gets them tangled up in that. And then eosinophils secrete toxins that kill parasitic worms specifically. So these three cell types, what they really do is they secrete something onto the pathogen, and which causes the pathogen to be, in effect, killed or neutralized. Then you have some chemicals that are released. One is called interferon, and interferon is specifically antiviral. So these are protein molecules released that are antiviral. They're naturally produced antiviral chemicals. And when your body is secreting these interferons, it can cause the symptoms that most people associate with a viral infection. So complement is something else. Complement is, these are proteins in your serum. They were named numerically in order of their order of discovery. They were not named numerically in order of how they function chronologically in the complement process. But what really complement does is it creates a complex on the surface of a cell which basically pokes a hole in that cell and causes it to lyse. But it leads to inflammation and fever in the host, which actually inflammation and fever are helpful in the fight against a pathogen. But complement is these proteins, and they're named, here's a picture here. They're named like C1, C2, C3, C4, C4A, C4B, blah, blah, blah. And the C stands for complement factor and then the number. But you don't have to memorize the numbers, but these are complement factors. So anything C with a number after it is one of the complement proteins. Ultimately, what the complement proteins do is create what we call the membrane attack complex, MAC, membrane attack complex, which basically they insert themselves into the membrane. This would represent the pathogen here. This is the thing that needs to be killed. And so these proteins, in a whole series of events, end up inserting themselves into the membrane, and that creates a pore, an opening. And usually you don't just have one of these on a cell, on a pathogen, you would get a lot of them. And so these things are creating holes in the pathogen, and that leads to, so it says the MAC drills a circular hole into the pathogen's cytoplasmic membrane, leading to lysis of the cell. So the complement pathway is one to kill a target cell. The way that the complement knows which target cell to kill is the target cell is marked with antibodies which have bound to antigens on that pathogen surface. So those antibodies attached to the antigen on the pathogen surface are like a little flag, and that helps the complement to know how to, or which cell to kill. So everything works together. And there's a lot of moving parts in immunology. There really are. Okay, let's talk about inflammation, because inflammation in most cases is actually pretty helpful. It's a non-specific response to tissue damage. And what you get is redness, heat, swelling, and pain. So let's say I actually slipped and I cut myself yesterday. I was outside and I grabbed a piece of metal, and when I was falling, I didn't fall down terribly, but and it kind of bruised and it kind of got swollen and red. It's not real big, but that's inflammation. So any small cut, anything like abrasion, scrape your knee, this will give you some inflammation. A lot of inflammation is helpful, but really there's two types. So if I'm going to be honest, the type that's helpful is the acute inflammation. Acute means short-lived. It serves its purpose and then it clears up. In an acute case, inflammation is helpful. In a chronic case, if you have inflammation that goes on and on and on and on, it can actually be it can cause damage to a much greater extent. So, if you have inflammation and you end up going to a doctor, he's going to want to know how long has this been going on. Because what he's trying to do is put it into one of these categories. If it's acute, maybe nothing needs to be done. If it's chronic, something does need to be done. So that's, those are two very different cases. So if you have acute inflammation, it develops quickly. Like when I cut myself, it kind of got red and kind of swelled up just a bit. You might not even notice sometimes, but it swells a little bit. It's very short-lived. It's beneficial. It's important to the second line of defense because part of inflammation is the release of chemicals that make the blood vessels in that area dilate, and that creates gaps between the cells that make up the wall of the blood vessel, and that way they are more permeable. And if they're more permeable, that means liquid, and especially phagocytes, so some of your white blood cells, can move out of the blood and into the tissue, diapedesis, and other factors which need to come in, like clotting factors and such, for tissue repair. So these are all good things. My little cut was able to scab over. The phagocytes are making sure that if there's any little bacteria in there, they get eaten up. And so this is all good. And now today it looks much better. So short-lived. In comparison, if you have chronic inflammation, if it goes on and on and on, in any way, then it can actually be much more, have a much more negative effect on the body. So that's why, if you have inflammation, a doctor is going to want to kind of know how long it's been going on, because he's trying to separate these two things. So what's happening when you have inflammation? You have these capillary beds. So capillaries are the vessels where cells and liquid can move in and out of the vessel. These are the vessels that are permeable. Your arteries and your veins are not permeable because they have a lot of muscle and other tissues surrounding the vessel. But the capillaries are fragile. Their walls are made of cells which can separate, so to speak, so that there's gaps between the cells, and so they're more permeable. So there are chemicals shown in green here which cause this dilation, this increase in permeability. And when they become permeable, you can see here's a monocyte going through the vessel, a normal vessel that's not dilated. But after the release of the chemical signals, there's a gap between the vessel wall cells, and the monocyte squeezes out through that space in that process called diapedesis. On this slide, I show a cut. So on the top left corner, you have a cut with bacteria. And this could be what happened to me yesterday. Then what's going to happen is the cells that are damaged are going to release several chemicals: prostaglandin, leukotriene, and histamine. All right. By the way, if you take an antihistamine, you're going to counteract the body's natural inflammatory response, which is not necessarily a good thing, because sometimes you want this, most times you want the inflammatory response to run its course. All right, if you take aspirin, you're going to counteract some of this. So, but anyway, so the cells release these chemicals. All right, so that's step 1 and step 2. All right, the prostaglandins and the leukotrienes are chemicals that make the vessels more permeable. They dilate the vessels. The histamine dilates the vessels. The prostaglandins and leukotrienes just make them more permeable. All of these together work to increase the blood flow at this site and to allow things to move into the tissue. Macrophages will move through the walls of the vessel. That's diapedesis. And it creates some swelling because of the increased volume of liquid there, right? And some heat. But all of this is important to the healing process. Clotting factors, you guys probably remember fibrinogen is cleaved. You've got your platelets that are caught in the fibrin, and phagocytes are still coming to the site. Leukocytes that are full of bacteria make pus. Ultimately, you get a scab and the whole thing turns down. All right, so let's talk about fever. There's been a lot of articles about this lately because fever historically has been defined as a body temperature above 37, and then they are arguing whether there's really such a thing as a low-grade fever or a high-grade fever, in the sense that, is there really any meaning whether or not you have a low-grade or a high-grade fever? Usually we only worry if you have a high-grade fever, a very high fever. But in any case, I digress. The reason the body temperature goes over 37 is that there are molecules called pyrogens that cause the hypothalamus to reset the body's set point. So you know that the body has a normal set point. By homeostasis, it tries to maintain that set point temperature. Pyrogens can be a lot of things. That's a very general term. It's anything that causes the body temperature to set higher. So some things that are released from bacteria, lipid A is a pyrogen. Cytoplasm of life's bacteria has chemicals that can act as pyrogens. Antibody-antigen complexes, chemicals released by phagocytes, etc. But as long as those pyrogens are there, the fever continues. The thing about fever is it activates, or it makes your interferons work better. And remember, interferons are antiviral. So if you have a viral infection, it's going to help. It does, of course, at a higher temperature. There are microbes that don't like to grow at that higher temperature, so it can slow down. It doesn't necessarily kill the microbes, but it slows them down. And it also enhances the activity of the phagocytes. So you've got a lot of positive effects of the actual fever itself. For this reason, you should not take drugs that bring down your fever, like Tylenol, every time you have a fever, because what you're actually doing is counteracting the body's natural healing process. You're counteracting the process of the immune response, because if you keep bringing down the fever chemically using Tylenol, then you may not actually get better. Or not as quickly. So you don't want to do that. If you've got a low-grade fever, you should let it go. You've got to monitor it, take your temperature every hour or two, but you don't want to just take Tylenol at the drop of every hat, because you're actually counteracting your body's healing response. Okay, so this is a summary. It looks terrible, but we're going to go through it, and you're going to see that it's not that terrible. The first line of defense, which is over here in one little box, and then the second line of defense, which they've spread out. And there's a lot of information here, and I do want you to know a lot of it, but I think once you look at what's actually written here, you can see the highlights. So the first line of defense are the skin and the mucous membranes and anything that they secrete. So the skin secretes sweat, the sebum has acid, mucous membranes secrete lysozyme, mucus. There's a certain amount of the skin sheds, the mucous membranes shed. And so there's the structure and the way these things work. It's your first line of defense. So keep your skin healthy as possible. In your second line of defense, this has to do really everything to do with cells that are in the blood. The only exception to that would be dendritic cells, which are in the skin. But this involves phagocytes, so macrophage, neutrophils, eosinophils. All right, and they should say dendritic cells. Those are cells that ingest pathogens and destroy them by phagocytosis. Then you have the cells that kill without phagocytosis. So remember the cells that come up next to another cell and secrete something onto them to destroy them. So eosinophils destroy helminths. Natural killer cells target mainly virally infected cells. And then neutrophils make those nets, N-E-T, which are fibers that catch bacteria. Then you have the chemicals, complement and interferon. I talked about those. Interferons are mainly antiviral. Complement is the system that makes the membrane attack complex, which is that drilled hole in the surface of the pathogen. I really didn't talk about antimicrobial peptides, so you can leave that out. Inflammation, there's a couple of chemicals, so histamine and prostaglandin and leukotrienes, which create swelling. They create increased blood permeability, blood flow to the site of a damaged area, a little bit of heat. And these are all good for healing a wound, for example, or an infection. And so inflammation. So this is where you don't want to necessarily take an antihistamine because an antihistamine is blocking the natural response. Now, if the inflammation keeps going on and on and on, then you can take an antihistamine. But you wouldn't want to take an antihistamine anytime you see the smallest amount of swelling. So I would not take an antihistamine for the little cut that I got yesterday, because what would happen is if I took it, it would stop the inflammation, which would stop the healing process. Now, if you have chronic issues or you have allergies, then antihistamine is a good thing because that's a problem that goes on and on and on. But for an acute inflammation, you would not take an antihistamine. Fever is where the body's temperature resets at a higher point, temporarily anyway. And it really helps with the interferons, which fight the virus if it's a virus. It helps with the phagocytes function. And again, you wouldn't want to take Tylenol or something like that to bring down the fever. Always. You don't want to take it immediately unless the fever gets super high or you have you're really worried for some reason. But you don't just give Tylenol immediately if it's a 99 degree Fahrenheit fever. You don't want to do that. Now, you do have to monitor, and then you do have to give Tylenol if your doctor says so, or if it gets to be a high fever. But as an academic concept, giving Tylenol immediately at any fever is actually counteracting the body's natural ability to fight. So that's an overview. Maybe make a little outline, rewrite it. I think it's helpful to organize the information.